Think of Redis as a lightning-fast digital locker. Unlike a traditional library archive that stores books in a basement, Redis keeps everything in a high-speed workspace, making retrieval nearly instantaneous. Redis uses a key-value model. Imagine a coat check. The key is your numbered ticket, and the value is the actual coat. You provide the ticket, and you get your item back immediately. Data in Redis lives in RAM, which is like working on a desk right in front of you. Traditional databases live on a disk, which is like walking to a warehouse across town every time you need a file. We start by including standard input-output and string libraries, which provide the tools we need to handle our data structures. The main function is where our logic begins. We define a key variable, which acts as our unique identifier for the data we want to store. Next, we assign a value to that key. In a real Redis environment, this could be a user session ID or a cached web page fragment. Here we define the TTL, or time to live. This tells the system how long the data should stay in memory before it automatically expires and is cleared out. Finally, we print our status to the console. This simulates the action of successfully setting a key in the Redis store. We begin by clearing the terminal and installing the Redis server. Using the non-interactive flag ensures the process runs smoothly without requiring manual input, which is ideal for automated setups or scripts. The package manager fetches the necessary files, configures the service, and prepares the environment for our database operations. The package manager handles dependencies like libgmalloc, ensuring Redis has the necessary memory allocation libraries. You see systemd creating symbolic links, which registers the Redis service to start automatically. This configuration ensures the server integrates correctly with the operating system's service manager before we begin our database operations. Next, we launch the Redis server in daemon mode. By using the daemonize flag, we instruct the process to run in the background, allowing the terminal to remain available for further commands. This is standard practice for production services, ensuring that your database continues to operate independently of your current shell session. The daemonize flag shifts the server into the background, detaching it from our current shell session. This ensures the database engine continues running independently as a persistent service, ready to handle incoming data requests without blocking our terminal. To confirm the server is active and responsive, we send a ping command using the Redis command line interface. A successful pong response indicates the server is running correctly. Now we store a simple key value pair. We set the session ID to logged in and immediately retrieve it to verify the data was saved successfully in the database. Finally, we manage the data lifecycle. We set an expiration time of 60 seconds on our session key, check the remaining time to live, and then delete the key entirely. The final get command confirms the key is gone, demonstrating how to effectively handle temporary data in Redis. The package manager finishes configuring the Redis binaries and systemd symlinks. When we launch the server, we see a memory overcommit warning. This is a common kernel configuration check. It ensures the operating system can handle Redis's memory allocation patterns efficiently during intensive write operations or background snapshots. The terminal displays the final output of our cleanup sequence. The one returned by the del command confirms the successful removal of the key, and the subsequent empty result from the get command verifies that the session data is now completely purged from the Redis memory store.